very much, Bob. It is a great pleasure to be here in Hobart again. I will say that whenever I come to Tasmania, I do feel like I'm coming home because it is a place that looks very much like where I grew up. And I have to admit, you guys do live in the beautiful part of Australia. Not that the rest isn't beautiful, but this is the beautiful part. Now, listening to the wonderful piece that Michael played and going to Mona earlier in the day made me reflect that what I'm going to be talking to you today is where science and art intersect. Because the universe is aesthetically very beautiful, and it's also challenging to your intellect. And I'm going to take you through a tour today of the universe and its life and its future. This is work that, as I said, I have worked on most of my life, and which eventually led to the awarding of the Nobel Prize to me and my collaborators for this work. Of course, in this journey, I'm going to be giving you a tour through the universe, and it is somewhat ironic that the reason we had the slight difficulties to begin with is because I managed to get lost coming here from Hobart 2 blocks. I just went over one and got confused. I will say Google Maps did not help me because it told me to go where I went. So, let's take a tour of the universe. The universe is very big. And to understand it, we're going to use the speed of light as our guide. Speed of light is very fast, 300,000 kilometers per second. That is 7.5 times around the Earth in each second. So now, let's use that to march out the cosmos. So for example, when Neil Armstrong took his one small step, we found out about it 1.5 seconds after it occurred, because that's how long it took the radio waves to travel from the moon, land just outside where I live in Canberra, and then be broadcast around the Earth. You may not realize it, but the sun is much bigger than the Earth-Moon system. It's 5 light seconds across. And the reason the sun appears so small is because it is so far away, about 8 light minutes in distance. Now, who here can tell me that they can go out tonight, I think it's cleared off, and point to the nearest star, Alpha Centauri? Raise your hand if you think you know where it's at. All right? So for the other 92% of you, be prepared to learn something new. If you go out tonight, Alpha Centauri, 4.3 light years in distance, is the brighter of the 2 pointer stars to the Southern Cross. So it is not difficult to see, and it's even harder to miss if you go out on a clear night. And so 4.3 light years is a long ways. To put it in perspective, if you were to think of the sun being a marble, and Alpha Centauri, which is a star very similar to our own sun, being another marble, then Alpha Centauri, if I were standing here as the sun, would be located in Canberra, where I live, with everything in between empty space. And that's particularly remarkable when you think that we live in a galaxy of 100 billion stars like our sun. Each one separated by that vast ocean, about 100 billion stars, and we are 30,000 light years from the center. Now the Milky Way is just one galaxy of many in the universe. The nearest galaxies are visible here in Tasmania. They're called the Large and Small Magellanic Clouds. They are small satellite galaxies. They orbit the Milky Way much like the moon orbits the Earth. They're small. They only contain 10 billion and 1 billion stars respectively. The first galaxy of any real size, and it's slightly bigger than the Milky Way, is the Andromeda Spiral, not so easily seen from Tasmania, 2 million light years in distance. Now we astronomers, we like to build large, expensive telescopes, as senators and representatives always like to describe them. And we like them because they allow us to look further and further away. And the most distant picture we've been able to take is this one, thus far, of stars and galaxies. Here we are looking back 12 billion light years. 12 billion years into the past. There are 5,000 galaxies in this one tiny little piece of the sky. Each one of these galaxies contains 100 billion stars, like the sun. This picture is 1/32 millionth of the nighttime sky. So although the universe is big, it isn't infinite, at least the part we can see. Because if I take 32 million pictures with the Hubble Space Telescope like that, I have seen everything in the sky there is to see. To put that in perspective, if each one of those stars has a planet, and we think almost every star in the Milky Way, and therefore the universe, has a planet. There are a few that don't, and many that have more than one, for example our own. Then you get to a number of planets likely to be in the visible universe, which is about 100,000 times more than the number of grains of sand on the planet Earth. It turns out we know how many planets there are in the universe more accurately than we do the number of grains of sand on Earth. So the universe is big, but it isn't infinite because we run out of something, which is time. We can only see back 13.8 billion years. Then we see this image. This image was released yesterday. This is an image of the universe when it was 380,000 years old. Here, the universe is not made of stars, it's not made out of galaxies. Instead, it is the entire universe is as hot as the sun, 4,000 degrees. And what you see here are sound waves rippling around the universe like little splashes in a pond. And those sound waves were created in the Big Bang itself. So before this, of course, is the time of the Big Bang. People often ask me, what came before the Big Bang? I don't know. Simple as that. It's the only answer I can give you. I don't know. But we do know, as I will show you, that something like the Big Bang happened. And how do we know that? Well, we know that through a bunch of deductive reasoning and observations that we've made over the last century. And it really began with someone that you will have no idea of, and his name is Vesto Melvin Slipher. Now, Slipher went through and took the light of stars and eventually galaxies and put them through a telescope. And when we astronomers look at things through a telescope, we tend to not just take pictures, although we do that as well. We spread the light into the colors of the rainbow. And we do that because we can learn a lot about what's going on when we do that. Every element, everything we know in the universe has a color fingerprint. Has a fingerprint of color which we can identify it. So for example, iron has a fingerprint, uranium has a fingerprint, helium has a fingerprint. Helium gets its name from the Greek word for the sun, because helium was discovered in the sun before it was on Earth. So what Slipher did is he looked at these fuzzy blobs in the sky called galaxies. He didn't know what they were, and when he spread them out into the colors of the rainbow, he saw that they had a color fingerprint, a fingerprint that looked almost identical to our sun. And so he knew they were made out of stars somehow. What he was surprised to see was that that color fingerprint was shifted red in color compared to the sun, by quite a bit. And he knew there was a physical effect that could cause it. It's called the Doppler shift. The Doppler shift you may encounter if you, for example, are going just a little too fast down the road from the airport, for example, into town, and suddenly you see a member of the Australian Federal Police in your rearview mirror, and they have their siren on. And as they speed up towards you, you will note that that siren is higher in pitch compared to when they go by you, because you actually were going the speed limit, and the person in front of you is the person who's speeding. And as they go past you, that sound lowers in pitch, and that's because the car is moving relatively fast compared to the speed of sound, about 1/10 of the speed of sound. And so as the sound waves get compressed, as it's coming towards you, they're raised in pitch. And as they go past you, they're stretched and lowered in pitch. Now, light is a wave analogous to sound. It's a little different, but it's the same basic idea. And so, if you have, for example, a galaxy coming towards you, then its light is compressed. It's made bluer. Light becomes bluer when it becomes compressed. If it happens to be moving away from you, then the light is stretched. It becomes redder. And so when Slipher made those measurements, and he saw that almost every object he looked at, these galaxies, had its light stretched red, it meant that all of these objects were moving away from us. And that was a cosmic conundrum. Because why would we be a specific, special place in the universe? Since the time of Copernicus, we've had this view that we are not special. We are a place like anywhere else in the universe. If we were on the other side of the universe, we should see exactly the same thing that we see being here on Earth, the Copernican principle. And yet here was evidence to the contrary. We seemed, at the very least, to be a very unpopular place that everything was going away from. Now, how did we figure that out? Well, we figured it out by measuring distances, it turns out. Measuring distances in astronomy is not straightforward. We cannot lay down a ruler between here and the nearest star or the nearest galaxy. Rather, we have to resort to how things appear. Now, fortunately, the further away something is, the fainter it appears, or the smaller it appears. And so, Edwin Hubble, who most of you have heard of due to the telescope named after him, in 1929, he had access to the biggest telescope of the day, the 100-inch telescope, which you can still see if you ever go to Los Angeles, to Mount Wilson, just outside of it. And he looked at Slipher's galaxies. And what he did is he looked at the stars in those galaxies. And when he looked at those stars, he found something interesting. The faster the galaxy was moving away by Slipher's measurements, the fainter its stars were. In other words, the further the galaxy was away, the faster it was moving. And he, with this data, just to show you Hubble's data, because Hubble is a famous guy, he's got a $5 billion telescope named after him. And here are his data. Bright stars, faint stars. Low amounts of stretch, so low velocity, high velocity. And you can see there's this trend. The further away you get, the faster the object is moving. And in 1929, he announced to the world that this meant that the universe was expanding. Now, it may not jump right out at you why he says that, so let me recreate a universe for you. Here is a universe, which thanks to the wonders of my computer, I am going to expand. This is the closest I get to play God. So, when I've expanded the universe, let's look at the before and the after. What do I see? Well, before and after. The nearby objects, when I've expanded the universe, they've moved a little bit. They'd be moving slowly. The distant objects, well, they've moved a lot. They'd be moving quickly. In this universe that I've expanded, the faster you move away, the further away you are, the faster you move away. Just like what Hubble saw. And furthermore, it doesn't matter where you are in the universe. I can overlay these images anywhere and I see exactly the same thing. If you don't believe me, go home, grab a balloon, put some little stars on it, blow it up, get your tape measure out, and measure the distance between all those stars as you blow your balloon up. You will see what Hubble saw. If you blow a balloon up, the further away you are, the faster you move apart as you blow that balloon up. So, we don't believe the universe is expanding just because of observations. Science is all about ideas meeting observations. You test your ideas with observation. And the idea comes from the theory of gravity that was Einstein's greatest work. Most of you think Einstein's greatest work was E equals mc squared. 2 years after that year that he did that, he had what he described as the greatest thought of his life. And it's not going to seem very great to you, that great thought was the following. That gravity, due to speeding up, acceleration due to speeding up, compared to acceleration due to gravity were indistinguishable. That is, imagine if you're in a box and you don't know if you're in space or you're sitting on Earth. You measure that you're being accelerated by 9.8 meters per second squared, which is what gravity does here in Hobart. Well, it could be that you're on Earth in a box, or it could be that you're in a rocket ship going faster and faster, accelerating at 9.8 meters per second squared. Einstein's thought was that those were indistinguishable. There was no way of differentiating. They were, for all intents, equivalent. A small, mundane thought. It took him 8.5 years to solve it. And his solution is known as general relativity. And general relativity predicts things. It predicts that space is curved. And space being curved made some predictions that could be tested. And one of those tests was that if you go and look at stars by the sun, they should be displaced. Space will be stretched around the sun a little bit, will be bent and curved. And so the stars, when the sun is there, will be in slightly different places on the sky than when the sun isn't there, because of this warping of space. Eddington, the most famous astronomer of the day, went out and tested this in 1919. And he did this by looking at an eclipse. And he went to one place, Principe, and then another person went to South America. And Eddington had clouds, and so he couldn't see any stars. The royal astronomer managed not to get his telescope in focus. Some irony there. But from this data, Eddington was a theorist. Eddington went out and measured the positions of these stars and showed to the world, at least he thought he did, that showed that Einstein was correct. Newton was not correct, and instantly Einstein became a hero. Now, truth be said, it is now believed that Eddington probably cooked the books. He probably didn't mean to. He was a theorist. We always say theorists should never touch data in my field. The real observations were done in 1922 here in Australia, in Western Australia, a fact that is not widely known here. And so Einstein's theory of general relativity was really shown to be correct with observations here in 1922 in Western Australia by 2 American astronomers. So with this new theory, Einstein went out to go through and see what he could do with it. And one of the first things he realized he could do is he could solve a problem that Newton never could with his laws of gravity, which is, how does gravity work in a universe that goes on without end? And this was something that literally drove Newton nuts. I had the opportunity of looking through Newton's books a few years ago, and I can attest that Newton, I think, really was nuts. He used to keep all of his mathematics out as many digits as he could fit on a page, like 50 digits. Think of what he could have done if he had only carried 4 or 5 digits. One page we showed was particularly gruesome, where he was trying to figure out how his eye worked and was sticking a needle in his eye and describing the observations. The page in front of me had Newton's blood all over it. I didn't have lunch after that. Anyway, Newton was an interesting guy. Einstein was also an interesting guy, and what he did is he went out and he solved cosmology, that thing that Newton could never do. And when he did it, he found something that was a surprise. His equations in 1917, when he did this work, showed that the universe should be in motion. It should be expanding or contracting. Unfortunately, this was 12 years before Hubble made his discovery. And so Newton looked around him and said, well, the universe doesn't seem to be in motion. My theory of general relativity is so beautiful. What do I do? Well, he did what every theorist does when their theory does not match the data. They come up with a fudge factor. And that fudge factor he called the cosmological constant. It was a term he put into his equations where space itself has energy, and energy and mass are the same thing to Einstein. They are equivalent as well. That's as E equals mc squared. And so it turns out, according to his equations, And he didn't just make this up, this mathematically comes out. If you add energy to space, gravity does not make things pull, it pushes. And so his idea is that the universe was born with this energy, and this energy would directly offset the gravity of everything and make space static, not move. Well, it turns out that, of course, 12 years later, it was realized the universe really was expanding. And so later in life, Einstein was quoted as saying that that was his greatest blunder. Now, Einstein's theory of gravity is a little different than the way Slipher was thinking about it when he measured the Doppler shift. When we look at distant objects, we're looking back into the past, and as light travels through the universe, the wave gets stretched by the expansion of space. Not so much that the objects are moving away from us, but rather that space is being created between us. A subtle difference. And so as light travels, the more and further away it is, the more space has a chance to expand, and the more the light is stretched. So imagine we have a universe which is expanding. Well, let's run it in reverse. What happens? Things get closer and closer and closer until everything in the universe is on top of everything else. The time of the Big Bang. If the universe is expanding, it is really almost inevitable that there will be a time of the Big Bang when everything in the universe is on top of everything else. It is only if the stars are literally being manufactured out of the ether, which was an alternative theory, that this would not happen. It is rather amazing to me that it was suggested many, many times that the universe was created in a Big Bang, but those were subsequently ignored. And it wasn't until it was observationally seen that afterglow of the Big Bang, when the universe was hot, that it was widely accepted. Those observations were made in 1964. So the universe is, if we run it back in time, smaller and smaller and smaller. So let's think of this as a graph. Right now, two galaxies are separated by some distance. I run the universe back in time. That dotted line is how fast the universe is expanding. The steepness of that line tells you how fast the universe is expanding. But you can see it also tells you when the Big Bang happened. It tells you how long ago it was that everything was on top of everything else. And so the steepness of that line, or how fast the universe is expanding, tells you how old the universe is. Now, that was such an interesting idea that when I went off to do my PhD thesis, I said, how big a question is it to answer how old the universe is? And here I am, 3 years, 11 months, and 4 days after I started my PhD thesis, but I wasn't counting, showing my PhD supervisor the answer, Bob Kirshner. And the answer I got was that the universe was about 14 billion years old. But I soon realized, now that I had done that, and I should say, I was part of a much bigger discussion. I do not get credit for measuring the age of the universe. Many people do, and I was part of the discussion. So let's make sure no one in the audience starts throwing tomatoes at me, because the one way scientists really upset each other is saying they did someone else's work. That is absolutely not allowed. So the problem is that the universe is a little more complicated than my first diagram. The universe I showed you, that line is straight. But what happens if the line is curved? Well, we expect the line to be curved because gravity fills the universe, and gravity will pull on the universe and slow it down. Very much like gravity of the Earth slows a ball down that I throw up in the air. Right? So the ball goes up, gravity slows the ball down, and eventually the ball falls to the ground. If I could imagine throwing the ball faster than the escape velocity of the Earth and there was no atmosphere, then that ball would not necessarily slow down a little bit, but it would keep going off to infinity. Well, the universe is very, very similar. Because if the universe is slowing down, or it's not, it does different things in the future. So imagine a universe which isn't slowing down. Gravity is very, very small. There's very, very little stuff in it. Then this universe will expand forever and ever, without end. It's a universe that goes on forever in the future. It is infinite into the future. On the other hand, a universe which has a lot of stuff in it, slowing down like the ball I throw up in this room slows down, that universe would reach a maximum size if it has enough stuff in it, and then gravity would take the universe and put it into reverse. And whereas both these universes start with a Big Bang, this second universe, of course, ends with a gonad gib. That's the Big Bang happens. So, in 1994, when I moved to Australia, I started thinking about problems. And it struck me that measuring the age of the universe is just the tip of the iceberg. Because I really hadn't measured the age of the universe. I could also measure its future. But there's more. And that's because, although the slowing down of the universe affects how old we think the universe is, it tells us the ultimate fate of the universe, it turns out it also tells us the shape and weight of the universe. So remember, space can be curved by Einstein's gravity. So a heavy universe that eventually stops expanding and goes into reverse is so heavy that space bends onto itself in a fourth dimension that's related to time. You're saying, I don't understand it. Well, okay. I don't understand very well either. I can write it down mathematically. But this is a universe, if I start here and I head off that direction, given enough time, I will eventually come back to where I stand. Space wraps onto itself in this fourth dimension. If you say, I don't really get how that works, it is analogous to Christopher Columbus going out around the world and expecting to come back. But truth be said, I have never met a sane person who can visualize 4 dimensions. And trust me, you don't want to be one of the people who can. So, the universe, of course, may not be heavy. It may be light. And a light universe naturally bends away from itself in the shape of a saddle. If you go out and make triangles in this universe, they end up having angles that add up to less than 180 degrees. In this universe, they add up to more than 180 degrees. If you go and do this experiment on planet Earth, which is this shape, but in 3 dimensions, our triangles on Earth add up to more than 180 degrees. Now you say, if I do that right here, and I say that to my geometry teacher, they're going to get upset and probably mark you down. But I want you to do the experiment of going off and do a triangle that is the scale of the planet Earth. Start at the, for example, at the pole and go down to the equator. You can easily make triangles that are greater than 180 degrees, but you certainly can't make one less than 180 degrees on the Earth. All right, and then finally we have the just right universe, that universe that's precariously balanced between the finite and the infinite. It has just the right amount of stuff, so space neither bends onto itself or away from itself. It's also just right because the theorists who try to understand the instant after the Big Bang predict that this is the way the universe should be. Just right. So, imagine an experiment where you go through and you measure how fast the universe is expanding over time. We can do this because remember, if we look at very distant objects, we're looking back in time. In 1994, I moved to Australia, and technology had just occurred that allowed us for the first time to do this experiment. We could go through and measure how fast the universe is expanding now and compare it to billions of years ago. If the universe was expanding at the same rate in the past as now, then we know that there was very little gravity, and that meant we had an infinite universe that was going to go on forever. On the other hand, if the universe was slowing down with a trajectory on this side of this line, then we knew the universe was heavy and was finite and was eventually going to end. On the other side of this line, well, gravity loses and the universe expands forever. So, how are we going to make these measurements? Well, it turns out with these big, expensive toys called telescopes that I like to play with, you still need the brightest objects in the universe to see them across the billions of years of space. And this is one such object. It's called a Type 1a supernova. So what is a Type 1a supernova? Well, to explain it, let me take you through a tour of the sun's life. 4.6 billion years ago, the sun was formed, and in 4 billion years, the sun is going to puff up and unfortunately destroy the Earth. I'm sorry for that, there's nothing I can do about it. The sun's center will collapse down to a tiny little star called a white dwarf star, about the size of the Earth. Now, if our sun was instead born as a binary star, two stars, that same process happens, except for stars are a lot bigger than Earth. They survive. And the second star, when it puffs up in its form of its life, it will make this star get heavier and heavier and heavier until it reaches 1.38 times the mass of the sun. And then it becomes a giant thermonuclear bomb. A bomb that is the size bigger than our sun. These things, when they explode, take 20 days to reach their maximum brightness. They shine 5 billion times brighter than our sun. They make 65% of the iron in the universe. The chairs you sit on here tonight were formed in these explosions. So these things, of course, because they are so bright, we can see them all the way across the universe. And a group in Chile, going through, starting in 1990, and these are people who I knew and did part of my thesis with, went through and started looking at these objects. And what they found is these objects weren't all the same. It turns out some made more iron and some made less iron. The ones that made a little bit of iron were fainter than the ones that made a lot of iron. But using this, they could calibrate how bright these things are so that they could measure distances more accurately. You can imagine if I'm looking at an object, a candle, and I make it further and further back away, it'll become fainter and fainter. But what happens if I'm comparing slightly different candles, one that's a little brighter than the other? That would cause an uncertainty in our measurement of distance. They managed to fix that problem. In 1994, just before I moved to Australia, Mario Hamui, who was a young student on that team, came up and showed me his version of Hubble's diagram, the expansion rate of the universe. And these were his dots. Now, compared to the other diagrams, all of his dots lie on the line exactly. And that's because they had found a way to make these things measure distances which were accurate to 6%. And to cosmologists who are usually happy to factors of 2, this was a major breakthrough. This team in Chile eventually discovered 29 of these objects, and they provide the fundamental basis for our work to measure the distance across the universe. But that was not the only other breakthrough. The other breakthrough was one of technology. Technology in 1994 was such that we had new telescopes, the first 10-meter telescopes. These are the Keck telescopes in Hawaii. And these telescopes were big enough, finally, for us to look at the light of these distant exploding stars, spread their light into the colors of the rainbow, and actually see how much the universe had expanded, how much it had stretched. It wasn't possible before this, because the telescopes simply were not big enough. The other one was one of electronics. In 1994, the first large digital detectors, 4-megapixel detectors, came out in 1994. One of the things that astronomy has done is they took these devices, charge-coupled devices, and took them from little things that really no one was using to the broad spread use within astronomy, medical imaging, and eventually consumer electronics. Now, I wouldn't say we invented them, we didn't, but we were the ones who got the whole thing going up at some scale. And that's one of the ways where basic research, such as what I do, contributes to society. So these 4-megapixel imagers in 1994, that doesn't sound very big, since my iPhone right now has an 8-megapixel camera. But this was 1994, when the fastest computer was a 100 megahertz Pentium, for those who remember it, something that was substantially slower than my iPhone. And the largest hard drives we had were 1 gigabyte, also substantially less than the flash memory in my iPhone. So it was really challenging back then. There was two teams that decided to work on this. One was based out of Berkeley. My own team was scattered around the world, and I led it here from Australia. As a 27-year-old postdoc, I was allowed, when I moved to Australia, to lead this team and given the resources I needed to do that, which was, I always say that if I had not moved to Australia, I would have never ever won the Nobel Prize, because I would have never been given that freedom had I stayed in the United States. And so we had a very competitive process of going out and looking at the universe. And that competitive process didn't mean we didn't have fun, but it did help the science we did. It allowed us to go out and do our science better, more quickly than we otherwise would have. So the challenge was one of sifting through all this data we could take with these massive detectors. Here is the image that we would have taken, and the challenge is to find the needle in the haystack, the exploding star. Because these exploding stars are very rare. They only happen in a galaxy like the Milky Way every 250 years. And so you have to look at tens and thousands of galaxies to find one. And our computers, which is what I was in charge of writing the software for, had to sift through this data and find one. And so here is one such object. This object, right here, is a supernova 5 billion years into the past. It exploded before the Earth was formed. And the way we knew that is we take two pictures. We take a before and an after. So in these two pictures, you can see in the space of 3 weeks, nothing became this object 5 billion times brighter than our sun. So to give you a sense of this, I'm going to take you to Chile on one of our runs, the Atacama Desert, at the CTIO 4-meter telescope. The CTIO 4-meter telescope, as dawn sets, we see Greg Aldering from the other team. He's silhouetted in black because, of course, he's the bad guy. And we shared these facilities because astronomers do share their toys with each other. We do normally play pretty well together. And we all use the same equipment if it's what we need to do our experiments. So as the sun and stars go by, we take these images, and my software is processing the data, looking for these exploding stars. But it finds lots of things. It finds asteroids. It finds things that aren't supernovae. And I have literally a sweatshop of other astronomers peering through the data, trying to separate out the things my software said might be to the things that really are. And time is of the essence, because 36 hours later, on the other side of the planet, we have the Keck telescopes, which are going to observe these things we're seeing in Chile. And so there we take their spectra. Here's Adam Rees, one of my co-winners of the Nobel Prize. And who's there? Saul Perlmutter from the other team. He was the leader of the other team and also a co-recipient of the Nobel Prize. Because, of course, they were using that facility as well. So we did have an intense competition, but we didn't necessarily go and show our data to them, but we did sit down and often have a beer afterwards, because this was very hard work. So what did we find? Well, at the end of 1997, this is what I saw for the first time, this data. Now this data, just to explain it to you, shows the expansion rate as a function of time of the universe. Each supernova measures the expansion rate at an age. And so these are the nearby objects that the Chilean team discovered in the 1990s. Each object has an uncertainty. That means that 2/3 of the time, that bar from top to bottom describes the answer that that object should give. 1/3 of the time, it's outside those bars. So you have to sort of make an average with your eye. But you can see, on average, these objects, you can't tell what's going on. That's why we had to look back in time. And what I saw when we looked back in time is that not a single object back in time was consistent with gravity winning and the universe being finite. But then I looked at the data and I said, well, some of them are consistent with the yellow part of the diagram, but on average, they clearly lie above the diagram. So we do statistical analysis, and the statistics of this sample said that 99.95% of the time, these objects lie up in the part of the diagram where the universe was expanding slower in this past and had sped up. People said, when you saw this, did you say eureka? And the answer was no. I was talking with Adam, and I said, what have we done wrong? That was the only reaction I had. After several months of checking our work, I was resigned to the fact we were going to have to tell the world, this is what our data says, and I figured I would be finding a new form of employment after that. Because, you know, when you go and tell the world that the universe is doing something it shouldn't, I suspected they weren't going to believe us. Little did I know, at the same time, Saul Perlmutter's team was getting the same answer and scratching their head about it. And so in 1998, both teams, after working independently for 3 long years, came up with the same crazy answer. And they were 2 papers. These are the papers we published. And that is the papers that eventually led to the Nobel Prize. And here we are together, the High-Z supernova team, all 20 of us, or 19 of us, together for the first and only time all together. We're a dispersed group. We work through the internet. The idea of the internet actually was born out of the military and NASA, but was first put into astronomy in civilian life. So that's another way in which astronomy has contributed. So, although we had never all been in one place at one time, we all knew each other and on a whole worked together one way or another. Now, the other team, of course, was there as well, and here they are together in Stockholm. So we had a great time for a week. And so most of you probably haven't been to a Nobel Prize ceremony in Stockholm. Let me give you a quick tour. You arrive. When you arrive as a Nobel Prize winner, they say, would you like to please come to the front, Professor Schmidt? You go out, and instead of going down the normal walkway, they have you go off onto the tarmac where you're met by a driver. My driver's name, Stig. I said, Stig. And he says, is there a problem with that? I said, no, I'm sure you'll drive us around the streets of Stockholm very quickly, which he did. So Stig, my driver, took me around for the week. You get to meet the king, who gives you a very nice gold medallion, which if you want to go to Canberra, mine is in Questacon, because my university, when they realized it was in my office, put it into a safe where I could not see it. So I figured everyone should see it. So it's great that Questacon have been able to host it. And in my case, they also met me a princess. So this is the Crown Princess Victoria. And you go to a giant banquet of about 1,700 people. And in my case, the princess was actually a surprisingly good conversationalist. She was 6 months pregnant, so this was her glamour first appearance to the Swedish public with a baby bump. So that was a very exciting night. Sweden has, it's really quite remarkable that Sweden has, this is their biggest event of the year, and they dedicate it to science. And the rest of the world owes them a great tribute to what they do for science. So, what pushes on the universe? Well, we only have to look to Einstein. His great blunder appears to be our great discovery. The problem is, we need to have about 70% of the universe be this stuff he thought, his fudge factor. Energy, being part of space, has to be 70% of the universe. So you can see why I was a little scared when I went on to tell the world about our discovery. I knew I was telling them what we think is going on is that everyone's missed 70% of the universe, and by the way, this stuff makes gravity push rather than pull. So we give this the name dark energy because whenever an astronomer doesn't know what's going on, we use the term dark. It's a euphemism. And dark energy is the way to describe this stuff that seems to be part of space itself. So, in order to make it work, we really need to have the universe be 30% stuff that pulls and 70% stuff that pushes. Needless to say, people wanted to go out and check this when we got our answer in 1998. And they have been doing so. The first big check was done here in Australia. This is a map of 221,000 galaxies up at Coonabarabran. Each galaxy is a dot on this thing, and you can see they form sort of a foamy structure. The shape of that foamy structure allows you to weigh the universe very accurately. And when they weighed that, they found out it was about 30% of the universe. There was an amount of stuff in the universe that can pull. They can only measure stuff that makes gravity pull in this experiment. And they found there was about 30% of it necessary to make the universe just right. When you go out and you measure how much the universe weighs, you weigh it compared to how much stuff it takes to make the universe become flat or just right. So they measured it was 30% of the way there with gravity that pulls. But they were unable to measure stuff that pushes. So the other measurement that they saw was that, but this was 5 times more gravity than we could account for from the atoms that we know are in the universe. So that stuff we like to call the other euphemism, dark matter. Stuff whose gravity we can see pulling, but we don't know what it's there. So what is this dark matter stuff? Well, we think it may be some undiscovered particle that, like a neutrino, can pass right through Earth. Those neutrinos really do exist. It has gravity just like atoms, but it's essentially invisible because the way we see things is because they interact with other things. This stuff doesn't interact with anything, so it's almost like it's invisible. Now, the other experiment, and this is an image that was released yesterday from the Planck experiment, but the first ones of these came out in the early 2000s. These sound waves rippling across the universe have a size that physics can tell us exactly how big they are in meters. And that is essentially the speed of sound times the age of the universe. And so these little bumps are 450,000 light years long. We know that number to better than 1%, just using physics we understand here on Earth. Now it turns out how big those sound waves appear matters how big they appear on the sky. And it's not as simple as you might think, because if space is curved, then the light wave rays travel on curved paths. So for example, this ruler, the red line here, appears exactly the same size as the yellow line. And yet, the red line is a much smaller ruler than the yellow line. In other words, things appear different sizes depending on the curvature of the universe. And remember, the curvature of the universe depends on how much stuff there is in it. Objects appear larger in curved finite space, just like your mirror distorts things when you look backwards. And so when you go out and you measure the geometry of the universe, what you find is the size of those bumps aren't this, they're this. And they're there to better than 1%. That is, we know the universe is just right to better than 1%. It's one of the most precise measurements we have in all of astrophysics. But this experiment doesn't care if the universe is made out of stuff that pulls or stuff that pushes. Anything that has gravity adds up in this. So we can do some easy subtraction. Everything adds up to 100% by that experiment. 20 or 30% of it is stuff that pulls, leaving us with 70% mystery matter. That same mystery matter, it seems, that we discovered that's pushing the universe apart. So what are we left with? Well, we're really left with quite a messy universe. It is a universe which is 5% atoms, the stuff we know here on Earth. It is 26% dark matter, this stuff that has gravity that pulls, but seemingly can go right through the Earth. It's 69% dark energy, the stuff that makes gravity push and seems to be part of the fabric of space itself. Now, those skeptics in the audience might say, if you got to make up 95% of the universe, doesn't that just mean you don't understand what you're doing? And that would be a reasonable summary, except we can go through with this model and predict things. We can predict what those sound waves look like in excruciating detail. Every test this model has faced, it has been able to predict the answer in advance. And that is what reality is about. It's about ideas that predict things. That's what science is about. And that is why we believe this model. All right. So I'm going to quickly do a little demonstration. And Bob, could I have you please come to the front? Now, using some great NASA technology, which involves a green bicycle tire, not fully inflated, some duct tape, and some blue tack, I have here an experiment. So what I'm going to have you do is hold on to this thing, and I am going to try not to hurt myself. I'm going to put a little tack. Now we need balloons from the back. So what I'm going to have you do is I'm going to have you do a little experiment where you're going to use this contraption to try to pop a balloon. Okay? So I want you to face the audience. So you face out this way. Now what I'm going to do is I'm going to spin this tire. Okay? Yes. And we're going to put the balloon right here, I hope. And you're going to, in one simple motion, go through and pop the balloon. My assistant here, can I have you just, Karen, can I just have you stand here? Okay, now I want you to, because he may hurt you, I'd like you just to step on it. Okay, and you just step on it there, and keep your hand out of the way, because there is a tack. Okay, so you stand there, and in one fluid motion you're going to, I'm going to start this thing going. Yeah, you hold on to it. So you're sort of like a Jedi Master here. Okay? Now, one fluid motion, pop the balloon. Yeah, that's okay, now, alright, so it's not so easy. Now, I'm going to show you why science is important. Okay? So, you've sort of broken my little device here, but we'll survive, I think. So could you start, I'll start this spinning. That's all right. So I get this going, and one of the beautiful things that you can do is you can just use physics. Oh, you let go. All sorts of interesting things with it that are counterintuitive. And one of them is this one. We'll try one more time. And we'll try not to cook the books this time, okay? So if I do this, rather than try to, you just let gravity do the work for you, okay? Okay. Thank you. Well, partially it was a cheap excuse just to entertain you and to get Bob up onto the stage. But science, one of the reasons we do astronomy is because it's aesthetic, it's beautiful. I've been to Namibia, I've been to the outback of Australia, I've been through the United States to poor places, rich places, and when I talk to 8-year-olds, they love to know their place in the universe. It is a universal thing. But the reason why we spend as much money that we do on it is because it is useful. And in the process of being able to look at physics, it can take something that's very complicated and the solution can become very simple. And that is what technology and knowledge is all about. So for example, this man you'll not know, he is the inventor of the World Wide Web. He worked at CERN looking for the Higgs boson. There is the first World Wide Web page in 1991. That is the single most valuable invention of modern humanity, coming out of basic research. Here in Australia, John O'Sullivan, one of my colleagues, invented Wi-Fi out of a failed attempt to look for Stephen Hawking's evaporated black holes. One of the most valuable patents in Australian history, if not the most valuable. These things come out of the work of the type I do. Now I can't tell you the dark energy I've discovered is going to invent a new toaster that is going to work better than anything you have. It almost certainly will not. I have no idea what it will lead to. But time after time after time, we have seen that basic research, curiosity-driven research, leads to positive outcomes for humanity. And that is why we do it. Of course, it leads to some bad ones occasionally, but that's an ethics problem rather than a knowledge problem. So, what is the future of the universe? So, the future of the universe is not dark matter. Because as the universe expands, the amount of dark matter and atoms, which were a small part of the universe, stays the same. So as the universe gets bigger and bigger and bigger, this stuff becomes less and less effective. Its gravity becomes diminished because its density becomes diminished. Dark energy, on the other hand, is part of space itself. As the universe expands, its force stays the same. And it's able to push harder and harder over time relative to the dark matter. And so this leads to a universe where, in the battle for domination of the universe, dark energy has won. So as the universe expands, more dark energy is made. It can push harder and harder against gravity, and eventually the universe runs away from itself, expanding more and more quickly over time. Our discovery indicates that that has just started about 5 or 6 billion years ago, but it is likely to continue forever into the future. And eventually the universe will be expanding so quickly that the creation of space happens even faster than light and information can travel through space. So the galaxies that we see today, their light, as it travels through space, will get stranded in the expanding cosmos and never reach us. The light of the most distant galaxies I showed you in that picture from the Hubble Space Telescope, the light those galaxies emit today will never reach us in the future. Now, you might say, what does that mean for us? Well, in this measurement we have made, that is the density of dark energy in the universe. It isn't very much, kilograms per meter cubed. The density of Earth is that much. So guess what? Dark energy is not very important here on Earth. The universe here quit expanding 13.5 billion years ago. We collapsed because we had a lot of gravity in this part of the universe. So we are not expanding, and we will not expand in the future. But our own little part of the universe, till this density of stuff drops below that density, will eventually collapse and form a supergalaxy. So the Andromeda Galaxy is one of the few galaxies in the universe coming towards us. It will eventually merge with us in a very spectacular display for future inhabitants of the Earth, 3.5 billion years from now. And we will live in this supergalaxy of the future. But when we look out of this supergalaxy into the future, we will not see anything because the rest of the universe will be accelerated out of sight to a place where we are no longer able to view it. We will see stars, but look out onto an empty universe. The reality is we don't really understand dark energy very well. So a theorist would say, until we understand that dark energy, anything is possible. So there is maybe a ray of hope there. Because dark energy may change and morph into something else. We do not know. But unless that dark energy very quickly changes, well, we're going to live in a universe which is at an ever-increasing rate going to expand, fade away, with the galaxies in it disappearing, leaving me and my future astronomers unemployed. So I think the universe provides a beautiful lesson for us here on Earth, because when we live our lives here on Earth, we have to realize that opportunities will pass us by and will fade away and have the potential of never returning. And on that note, I will stop. Thank you very much.
Recycling milk bottles, increase in power prices, and the decrease in the number of politicians. But I know that since 1864, that is the most erudite exposition on the universe we live in and which we are part of ever in this great hall. And I thank you so much for that, Brian. I'm tempted to quip a little by saying, you know, the scientists might have dark energy, but for a lot longer we've been producing dark energy chocolate up there in Cadbury's. And Tasmanians first. I'll get you a block tomorrow on the way to the sticks. It's fascinating, isn't it? You get a feeling from a talk by a great mind in the universe, as we've just heard, about this universe. We can't come to conclusions, but we get a wonderful insight into what we are and what we are part of. And for that we have to be extraordinarily grateful. And I suppose those scientists in the future, Brian, when they can't look out there because there's nothing to see beyond the stars, will be grateful for all the recording done now when we could see it. The insight of the ancient elders of 2013. I've really thoroughly enjoyed tonight, and I'm going to ask the Leader of the Parliamentary Greens here in Tasmania, Minister for Education, Nick McKim, if he'd come up and offer you a vote of thanks. Thank you.
Thank you so much everyone for coming along tonight. Brian, that was a fascinating presentation. It was intriguing, it was highly interesting and ultimately inspirational, and I'm sure I speak for others here tonight. And when I walk out of this room tonight, I'll have a better understanding of where we all sit in the universe and ultimately my place in the universe, and that is the most fantastic gift. So thank you very much. And speaking of gifts, Brian, if you would come up one more time, we have a book on our fabulous Tarkine, and as I present this, ladies and gentlemen, could you show your appreciation in the appropriate way to the best. Thank you, ladies and gentlemen. There is, I believe, a cup of tea and a chat at the back. Just very quickly, at the Greens National Council tomorrow morning, there is an exploration of the role of politics in science. So if any of you are interested in science, and I presume many of you are interested in politics, please do come along. It will be an interesting discussion, and Bob's just handed me a note which says there is the 30th anniversary of the World Heritage Listing. Following the Franklin blockade and a celebration of the value conservation has delivered to Tasmania. It'll be the weekend of the 19th and 20th of July, so please keep an eye out for details and save that weekend, the 19th and 20th of July. Wouldn't it be great, ladies and gentlemen, when we get to June this year, when UNESCO consider a World Heritage extension of 170,000 hectares, to be able to celebrate that as well on the weekend of the 19th and 20th of July. Thank you all so much for coming along tonight. Please join us for a cuppa and a chat with many of us who will stay on for those things. And once again, thank you so much for coming on.